Okay, so we're going to jump to chapter 10 as our first chapter for unit 3. And we're going to get into something called chemical bonding. Now, chemical bonding is when you have two atoms coming together. When they come together, they become more stable. So it's very important to understand, like my theme in this class is stability. So if they're not more stable coming together, they won't do it. Now, there are two general types of bonds. There's an ionic bond and a covalent bond. An ionic bond Lewis postulates an ionic bond will actually have a transfer of electrons. So whenever you think ionic, it is a transfer of electrons. When we have a transfer of electrons, that means that one of them is going to be deficient in electrons. The other is going to be a surplus of electrons. The one that's deficient of electrons will become positively charged. So one is going to be deficient, one's going to have a surplus. The deficient one is going to be called a cation, positively charged. The surplus one is going to be called an anion, and it's going to be negatively charged. Typically, because metals, remember on our periodic table, most of the elements are metals, they tend to lose electrons and become cations. The nonmetals in the top right tend to gain electrons. So a typical ionic bond is a combination of a metal and a nonmetal. Now, the reason we gain or lose electrons, again, is for stability. And that stability is gained by having a full shell. Frequently you hear about the octet rule. The problem with the octet rule, it isn't always 8 electrons. Sometimes it's 2, sometimes it's 12. But they always talk about 8 electrons. So I like to say, instead of an octet rule, I like to say the full shell rule. Okay? Because then it applies, it doesn't matter how many electrons, as long as the number of electrons fulfills the full shell. For example, in period 1, you can't have 8 electrons because there aren't enough. It's hydrogen and helium, and the maximum helium can have, which is a noble gas, is only 2. So that octet rule is inapplicable to period 1. So, but the full shell rule does apply. So in other words, hydrogen if it gains 1 electron, it becomes that. That means it has 2 electrons, full shell. H minus is called hydronium ion. Okay, so again, the idea is gaining or losing electrons to emulate the noble gases or a full shell. Okay, so whenever you see that octet rule, think in your mind, it's not really octet rule, it's really full shell. Does that make sense?
Yes, thank you.
Okay. All right. If we look at a, this is kind of a Bohr atom representation. We have this outer valence electron combining with an outer valence electron of chlorine, in where we have now a full shell. Okay, and notice the noble, or excuse me, notice the core atoms, or excuse me, the third time's a charm. Notice the core electrons don't do anything. They're in black. Okay, so we have the core electrons of sodium, which are these guys here. Those don't change at all. And again, because core electrons are extremely, extremely stable. Okay, so we look at group one. Group 1, 2, 3, 4, 5, 6, 7, 8. And these are A. And these are B down here. We don't tend to look at the B's in terms of groups. They have the same kind of tendencies where they're, excuse me, the valence electrons are the same within the group. But they usually refer to groups 1A and 2A and 7A and 8A a lot. Okay, and this tends to lose one electron, group 2, 2 electrons, 3 electrons, no electrons. This one, -1, -2, -3. Okay, so carbon, group 4, does not tend to form ions at all. If they form, they're extremely unstable. What group 4 does is it forms covalent bonds instead. Okay, so Lewis, Dr. Lewis, a long time ago, 150-ish years ago, said, if we represent the valence electrons only, we can start putting together some meaning. When you have a formula like this, it doesn't connote any kind of structure. It's just how many carbons in relation to hydrogens are there? Well, the ratio is 4:1 of hydrogens to carbon. That's all it really says. It doesn't say anything about how they're organized or anything else. So what Lewis says, if we look at taking the valence electrons, mainly of the first couple periods, and maybe even period 3, but no more than that, what do the structures look like? Now, these valence electrons are based upon the electronic configurations. Notice, for example, oxygen has got 2 pairs, 2 singletons. 2 pairs, 2 singletons. Now notice here the pairs are opposite. Here they're adjacent. That's equivalent. You can move the pairs and singletons around for convenience as long as you keep the pairs of electrons together. Okay, so before we go on here, let's look at doing some simple Lewis dot structures. Now, what I've done is okay, so we're looking at CH4. So step number 1 is, so this is going to be okay, so we're gonna use this, the Lewis dot structure process. Okay, so step number 1 is put the most, I'm going to say, versatile atom in the center. That is the most single electrons. Okay, so let's look at CH4. Okay. See, where's carbon? Here is carbon. Okay, carbon is got 4 singletons. Hydrogen has 1. No, hydrogen's not here. Anyway, okay. So in the case of CH4, we're going to put carbon in the middle because it's got 4 singletons. Hydrogen has 1. Number 2. Put the single singletons, that means the one with 1 electron only, around the most versatile. Yeah. Okay. So in this case, hydrogens are singletons, so we're going to put those around carbon. So here we have carbon with its 4 singletons. Now I'm going to be putting a whole bunch of worksheets on to practice Lewis dot structures. And I don't think I've done that yet, but I'm going to put them on right when class is over today, just to give you lots of extra practice on this. Okay, and then it says put the singletons around the most versatile atom. Okay, that's the hydrogens. Okay. I'm just going to put them around. All right. Step number 3 is connect all atoms with at least one bond of 2 electrons. Okay. So a bond is considered a pair of electrons. A bond is considered a pair of electrons. Notice I said that twice, very important. Okay, so here we have, no, it says connect all atoms with one bond. Okay, boom, boom. Oh, okay. Are there any singleton electrons left over? Okay. Let's look over here. Are there any non-bonded single electrons left over? No. Okay. If so, connect them. But we don't have any, so we're not going to worry about it. Okay, step 5 is check to see if each atom has a full shell of electrons. Okay. Now remember, this is a shared situation. Okay. So how many electrons does carbon have that's shared? Well, we have 2, 4, 6, 8. Is that a full shell for carbon? Yes. Check. What about for hydrogen? How many hydrogens require a full shell? 2 electrons, right? So each hydrogen has 2 electrons. So boom. Okay. The next check. Okay, check to see if each atom has a proper number of bonds. Okay. So here we have number of bonds. Okay, so we need to fill that in. Okay. So hydrogen has 1 bond. Most things have 4 bonds. Okay, so let's check now. How many bonds does carbon have? Carbon has 4 bonds. Now we can have a double bond and a triple bond as well. If it's a double bond, that's 2 pairs of electrons. A triple bond would be 3 pairs of electrons. So a triple bond would involve 6 electrons. A double bond would involve 4. A single bond would involve 2. Step 5 and 6 is the ultimate check. If these are fulfilled, we have a legal structure. Now, sometimes you can have multiple structures with the same formula be legal. So I'm going to do a whole bunch of examples here, give you an idea of what's going on here. Okay, and it always starts with a formula. So let's look at something called formic acid. Formic acid is when a red ant bites you, that's what it injects into you, is formic acid. Okay, so that's what formic acid looks like. Okay, these are the same formula. 2 oxygens, 2 hydrogens, 2 oxygens, 2 hydrogens. Both those are legal formulas for formic acid. Okay, so let's look at our rules here. Step number 1 is put the most versatile atom in the center. Okay, we have, now hydrogen is always a singleton. Hydrogens always go on the outside because they only have a single. Okay, so what do we have left over if we don't look at the hydrogens? We have carbons and oxygens. Which is more versatile? Which has more singletons, the carbons or the oxygens? The carbons do. So that means the carbon goes in the middle. Now, again, the purpose of doing a Lewis dot structure is to take, I'm going to reiterate this, to take a formula and make a structure. Okay, so we're taking a formula, making a structure, and it's based on the valence electrons. Okay, so carbon has got 4 singletons. Oxygen has 2 singletons and 2 pairs. And there are 2 of them, so we're just going to stick them. Let's do it in a different color. Let's do, now we can stick it anywhere we want. Doesn't matter. I'm just going to put it on one on each side. Now, the pairs don't bond because there are already 2 electrons. Only the singletons are going to bond. So I'm putting the pairs on the outside because they're not going to bond. Okay, so and then we have 2 hydrogens as well. Okay, is everyone okay with what we're doing now? Now, this is probably the first time you've seen this, but what we're doing is we're taking a formula and we're trying to make some structures out of it. Okay, and remember, sometimes we can make multiple structures since they'll have a legal Lewis structure because number 5 and number 6 are obeyed. Okay, so step number 2 is, step number 3 is connect all the atoms with at least 1 bond. Okay, so let's do milk. So here's 1, and backwards. Collect this, collect that. Okay, and let's connect up. And we have to connect up the hydrogens yet. We haven't connected up the hydrogens. Let's connect the hydrogens. This hydrogen here can connect here, or here, or here, or here. Okay, those are all candidates to connect. So let's connect this hydrogen to that one. And then let's connect up this hydrogen to that. Okay. So we connected everything with at least one bond. Okay. Is everyone okay with that? Okay, so number 4 is, are there any singletons left? If so, connect them. Okay, so we do have some singletons left over, don't we? We've got this singleton here, this singleton here. Now I want to add a little note to our number here, and but not to the same atom. Come on, give me a break. Okay. We can't attach, we can't do it to the same atom. So what we've done is doesn't work. Okay. Does everyone understand why we can't, why this doesn't work, what we've just done?
Is it because it leaves the two singletons unpaired?
Not only, yes, but also the only way we can pair them is to the same atom. That's the problem. So we have to redo this setup a little differently. Okay. All right. So I'm going to erase all the yellows here and we'll start over here. And do this a little different. So what we just did, and this is why you use pencil with a big eraser, so you can redo this. Okay. All right. So going back up to step 3 here, connect all atoms with at least one bond of 2 electrons. Okay, so let's redo the bonds, not the same way since it didn't work. Okay, so let's do them differently here. Okay, well, let's see, let's connect that singleton with that singleton. Oh, I don't know, let's connect that with this. And let's do this. Okay, so we've connected up. The oxygen has one bond to the carbon right here. This carbon goes over to the other oxygen with one bond. The hydrogen connects up with one bond to the oxygen. This hydrogen connects up with one carbon. Okay. We've done the same thing, we just did it differently. Okay, now, next question is, are there any singletons left? Yes, there are. And we have a singleton here and a singleton here. Notice now, they're not on the same atom. We have singletons unpaired, but they're not on the same atom. So now we can connect them together. Now, we ask the question again, are there any singletons left unpaired? No. So now we go on to the validation steps, 5 and 6. Okay. Does each atom have a full shell of electrons? Okay, now we're counting pairs as electrons. So let's look at the oxygen here. Okay, we've got 2, 4, 6, 8. Does everyone see where I got 8 electrons for the oxygen? Does anyone not see how I added those up? Okay, same over here on the right side. You have 2, 4, 6, 8. So oxygens are in good shape. What about the carbon? Carbon's got 2, 4, 6, 8. Carbon's in good shape. Hydrogen needs 2, or excuse me, oxygen needs 1 pair of bonds with 2 electrons. So we have 2 and 2. So the hydrogen's in good shape. Okay, so the number of bonds. Now what happened to this? Let me see here. Okay, and does each one have the proper number of bonds? Okay, so oxygen has 2 bonds. Oxygen on the right has 2 bonds. Carbon's got 4 bonds. Hydrogen has 1 and 1. So that's validated. So this is a legal structure. Now, after we get a legal structure, what we do then is we substitute a solid line for each bonding pair of electrons. So we get all this stuff worked out, then we redraw it a second time. Now notice the carbon oxygen here has 2 double bonds. And we have 1 bond here. And we have 1 bond to the oxygen. And that oxygen bonds to the hydrogen. Now, depending on how you drew the double bonds and stuff, your structure could also look like, if we flipped this horizontally, depending on how you drew it, you may end up something like this. Okay, these are equivalent. Okay, so this is how we went from the formula to an actual structure. Now, once we get the actual structure, we can start predicting. We can look at that and we go, oh, that looks like an organic acid. So now you can test this chemical to see if it has acidic properties. If it has acidic properties, then maybe this is in fact an acid. Okay, are you guys so far? Is this making sense?
It is, but I definitely want to go through some more examples.
Oh, yeah, for sure. I'm going to go through, I'm going to spend the rest of the time on doing examples for you. Now, the other thing is, depends on what book you're using, they will tell you a little different procedure. My procedure is based upon very simple approach, and it works every single time. There's another way to do it where you count total valence electrons, and it's much more complicated than this. This is a very simple approach, and it works. I've been using this since 1974, and my students like this approach. But there are 2 other approaches as well. So you can look at the other approach and choose which one works best for you. You'll get the same result. Excuse me, I haven't coughed all day until I started lecturing. Okay, so let's do another example. Now I'm going to do an example where there are going to be two legal structures. C2, O2, H6. Draw a Lewis structure. Now I'm going to ask you to draw two legal Lewis structures for this one. So let's start with one of them. Okay, so we have carbons, oxygens, hydrogens. Which is the most versatile, or which one has the most singletons? Carbon. Put those in the center to start with. Okay. Okay, and then start with that. The hydrogens are going to put on the out. They're going to surround the outside. And then we need the two oxygens. And let's put them, I don't know. Okay, so that is step one. Step two. Step three is connect all the atoms with at least one bond of two electrons. Well, two carbons together. Okay, what's wrong with what I just did?
There's
The
still
oxygen.
I don't know, you both spoke at once.
there's still two, there's still the oxygen electrons are unpaired.
Yeah, I left off oxygen totally. It's like, all right, so obviously this is not going to work. I've got to somehow do this differently. Okay, well, let's connect the hydrogens through the oxygen here. That. Same down here. Let's connect the hydrogen . Okay. So how are we doing? Is everything hooked up with at least one bond? Yes. Everything has one bond. We didn't leave anything out. We don't have any singletons left over. Okay. So let's look at now full set electrons. Okay. So the hydrogens need two. Hydrogens all have electrons. Carbon needs 8, 2, 4, 6, 8, 2, 4, 6, 8. Oxygen needs 8, 2 pairs, 2, 4, 6, 8, 2, 4. So everything's in good shape. Number of bonds, oxygen needs 2 bonds, hydrogen needs 1, carbon needs 4. So all the checking marks are done. 5 and 6 are done. That means we have a legal structure. So now we're going to fill in with the solid lines. So we're going to go. And notice how I drew the oxygen. Right here, I've got the pairs together. Here, I've got them separated. Remember, we can move them around. It doesn't matter as long as we keep the pairs together for convenience sake. Okay? That's one way of doing it. It's a legal structure. Now let's draw another legal structure. Now these structures, I can flip them horizontally. In other words, I can do these are the same structures. Same structures. By the way, it needs to be H. Know about this stuff. Okay, so let's do one totally different. In other words, one where this structure has the carbon with two oxygens attached. What if we were to draw a structure with only one oxygen attached to each carbon? Okay. Need to attach everything up. Now, in this situation, I attached over here on the left, I attached both oxygens to one carbon. In this situation, I'm going to do it this. Now, notice what I did, what I do wrong. Now, I'm telling you I did something wrong. So what do you think it is? Step number 3, connect all atoms with at least one bond of 2 electrons. What did I do wrong?
You still have leftover electron.
True. We have some singletons there, right? This hydrogen over here is not connected to anything. And look at this here. I have 2 hydrogens connected to one electron on the carbon. So that's wrong for sure. Right over here. So we have to get rid of that. And where can this over here on the right, where can this guy here go? Well, it can connect up with this hydrogen over here, this here. Problem is it's on the wrong side. So what we're going to do is we're going to, instead of do this, we're going to connect up this like that. And now this is more convenient. We could have drawn this around, but that's would have worked as well, but it was kind of hokey looking. Okay, so we still have a problem, and we have the problem is back over here on the left, these hydrogens. So if we connect up this one hydrogen to the one, oops, here, we have a singleton here, singleton here. So let's take and go like this and like this. Okay. So basically we've got this oxygen connected to the carbon, a hydrogen is connected to the oxygen, oxygen is connected to the carbon. Same down here. Hydrogen goes to oxygen, oxygen to carbon. Let's check for full shell. Carbon needs 8 electrons. We have 2, 4, 6, 8. Carbon 2, 4, 6, 8. Oxygen 2, 4, 6, 8. 2, 4, 6, 8. So that's fine. Carbon needs 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Oxygen needs 2 bonds. 1, 2, 1, 2. Hydrogen needs 1. So this is a legal structure. So the next thing we do is we fill in the yellow bond with solid lines. Now see how these two differ? And these are both legal structures. By the way, whenever we have an OH group, that's called an alcohol. So we have 2 alcohols, and they're called diols because there are 2 alcohols. We have 2 OH groups per set of carbons. But these are not the same molecule at all. They're both alcohols. They'll display alcohol properties, but they're not the same molecule. There's another legal structure we can draw as well. Are we okay with, does everyone see the difference between these 2 molecules? The differences lie here. Where on the left, we have 2 OH groups attached to a C. On the right, we have each carbon gets 1 OH group. Okay, so we're going to do another one yet. And these are legal. These are legal Lewis structures. Okay. Let's try another one. Only this time I'm going to put the hydrogen or the oxygens on the same side. Okay. So we're going to do now, we're going to connect everything with 1 bond. Okay, so we have an interesting situation here. So what we're going to do is we're going to attach the oxygens together. Okay, so everything's connected with 1 bond. All right, is this legal?
can the carbon singletons match with themselves?
But it's a different carbon. Not the
Okay.
same carbon. So to answer your question, yes and no. As long as they're
Okay.
different carbons, it's not the same atom.
Got it. Thank you.
So this here is that's fine. Any other issues? Have I fulfilled number 3?
It looks good to me.
There's only one problem. We don't have one molecule anymore. We have 2 molecules.
So do the rules become different?
Yeah, because we want to have one molecule, because the formula is that's the formula for one molecule, not 2 molecules. So we've connected everything with one single bond, but we haven't connected them together. In other words, we created 2 separate structures independent of one another. There's no commonality between this down here and above. There's no bond there, okay? So this will not work.
If we disconnected the 2 lower carbon electrons and connected those with the hydrogen, would that?
Then we'd leave out
Change
the
anything?
oxygens. So let's
Oh, yeah.
so let's kind of rethink this, okay? So I'm going to start over. Oops. This is why pencils and big erasers are good. Okay, so I'm going to have my carbons here. Notice I didn't put the carbons close to one another. We're going to stick the oxygens in the middle this time. Okay. So see how that's different than these guys? Here we put the carbons close to one another. Here we put the carbons outbound of the oxygens. So let's start connecting these up. Okay. Do we have any singletons left over?
No.
No. And do we have everything is a one big molecule, no 2 separate molecules, right? Okay. We have no singletons left over. Let's look at the number of bonds. Carbon needs 1, 2, 3, 4, 1, 2, 3, 4. Oxygen needs 2, 1, 2, 1, 2. And then the hydrogens are all. So that's legit. This is called a peroxide, by the way. So we have an alcohol. Peroxide. Similar to hydrogen peroxide, you use for disinfecting things. Peroxides are very anti-life because they're really good oxidizing agents. And when things get oxidized, things don't work anymore. That's why when you want to kill something, you oxidize it. Okay, so 3 legal structures, same formula. So these are called isomers. Same formula, different structures. And usually, different chemistry. Not all the time, usually. So some isomers have identical chemistry. Most of the time, they don't. Okay. So before I close, I want to do one more. Does this make sense in this isomer where we have these 3 structures are very different? Very, very different. Yet they all have the same C2O2H6 formula. And that's what Lewis wanted to fix. You know, they had processes where they could come up with a formula, but then they couldn't figure out where to go from there. So by drawing these various structures, you can now say, does this act more like an alcohol or a peroxide? You can do chemistry, and nowadays you use instruments to do it, but in the old days you use wet chemistry methods. For example, you can take a peroxide and put it in the presence of something, and if it changes color, then it's oxidized. Oh, then it's a peroxide then. Or you can take an alcohol and do some experiments to see whether it behaves like an alcohol. And then you could narrow down the structures. And for example, if it behaved like an alcohol, you could eliminate the peroxide. If it behaved more like a peroxide, you can eliminate the 2 alcohol structures. And that's what chemists did back in the about 100-ish years ago, well, maybe 90 years ago, before they started really getting into instrumentation. Instrumentation can tell right away between these structures. Use something called spectrophotometry, and you can use infrared. You can shoot infrared in there, and it'll behave differently based on the structure. And you'll get a printout, and the printout will be like a fingerprint of what the structure is. Now, when you finally take OChem, you will do a ton of instrumentation analysis. You will look at something called nuclear magnetic resonance. You'll look at infrared spectrophotometry. You'll look at visible, ultraviolet, numbers of instruments. Lots and lots of instrumentation. You'll see how valuable that is to determine structures. Okay, let's do one more, and then we'll pick up on Wednesday. Okay, so let's do. Okay, C2O2H4 as opposed to H6. Okay, so do our carbons. And there are like 5 structures to this. I'm going to do one for you. And what I'd like you to do is try some more. And then on Wednesday, I'd like to pick up here and finish off doing the alternate structures that fulfill this. But I'd like you to come up with 2 more structures from the one I'm going to do. 2 more structures. There are about, I believe, about 5 different structures that fulfill this for in terms of being legal. Okay, so okay. So here are carbons, oxygens, and hydrogens. So let's connect them up. That and these 3. This and that. Okay, so everything has 1 bond, 1 pair of electron bonds. And then the question is, do we have any singletons left over? What do you think? Any singletons left over?
Yes, the carbon and oxygen.
Yeah, exactly. Right here. Exactly. Okay, so we've got everything connected up, no singletons left over. Let's make sure it's by the rules. Carbon has 4 bonds, 1, 2, 3, 4. 1, 2, 3, 4 for the carbons. Oxygen needs 2 bonds, 2 and 2, and then our hydrogens are all 1 bond. Full set. Carbon needs 8 electrons, 2, 4, 6, 8, 2, 4, 6, 8. Oxygen needs 8, 2, 4, 6, 8, 2, 4, 6, 8. Hydrogen needs 2, 2, 2, 2, 2. So now it's a legal structure. Let's fill in the bonds with solid lines. This is called acetic acid. And if you dilute it with water, it's called vinegar. Now, there are other ways to draw this structure. This happens to be, of all the structures, this is the one that's the most stable, but there are other legal structures. And I would like you to try between now and Wednesday doing some more structures with that C2O2H4 formula. At least 2 more. Okay. All right. Are there any questions about the process to do a Lewis structure? Okay. All right. So what I'm going to do is I'm going to add some additional worksheets in modules, and that'll allow you to get some more practice as well as the what's in the official worksheet. Okay. You guys are kind of quiet today.